Hi, Assalamualaikum everyone. Now I will explain the topic equilibrium of bodies in system of force. So basically, equilibrium is all forces acting on object are balanced. When forces are balanced, the object will remain at rest or move at a constant velocity because there is no resultant force. For a body in equilibrium, we can see in the slide, which is Fs or total resultant forces equals to 0 and Fy or total vertical forces equals to 0. When only three forces act on a body and the body is in equilibrium, we can use Lami's theorem instead of resolving the forces into the x and y components. This method is simpler and faster for solving equilibrium problems using three forces. So what is Lami's theorem? Lami's theorem states that if three forces acting at one point are in equilibrium, each force is proportional to the sine of the angle between the other forces. Another important point is that the three forces must form a complete triangle, which is called the triangle of forces. If they can form a closed triangle, it means the resultant force is 0 and the body is equilibrium or is not moving.
This question is about the equilibrium of concurrent forces. We are given a system of three concurrent forces that is in static equilibrium. The forces are 12 newtons, 8 newtons, and an unknown force A. The 8 newton force acts at an angle of 60 degrees above the horizontal 12 newton force, while the angle between force A and the 8 newton force is represented by theta. Our task is to calculate the magnitude of force A and the angle theta. Since the system is in static equilibrium, the three forces must form a complete triangle of forces. This allows us to apply the cosine rule first to determine the magnitude of force A. The angle inside the force triangle is 120 degrees, which is obtained by subtracting the given 60 degrees from 180 degrees. Now we use the cosine rule. A square equals 12 squared plus 8 squared minus 2 multiplied by 12 multiplied by 8 multiplied by cosine of 120 degrees. And next we substitute the values. A square equals 144 plus 64 minus 192 multiplied by negative 0.5. Since the cosine of 120 degrees is negative 0.5, a square equals 208 plus 96. A square equals 304. Taking the square root, A equals the square root of 304, which is approximately 17.44 newtons. After finding the magnitude of A, we use the sine rule to calculate the angle theta. The sine rule is 8 divided by sine of alpha equals A divided by sine of 120 degrees. Since the interior angle opposite the 8 newton force is 180 degrees minus theta, we substitute 8 divided by sine of 180 degrees minus theta equals 17.44 divided by sine of 120 degrees. Rearranging the equation, sine of 180 degrees minus theta equals 8 multiplied by sine of 120 degrees divided by 17.44. The value of sine of 120 degrees is 0.8660. So, sine of 180 degrees minus theta equals 8 multiplied by 0.8660 divided by 17.44. Sine of 180 degrees minus theta is approximately 0.39972. Taking the inverse sine, 180 degrees minus theta equals the inverse sine of 0.3972, which is approximately 23.41 degrees. Finally, theta equals 180 degrees minus 23.41 degrees. Theta is approximately 156.59 degrees.
Now let's talk about what happens when there are more than 3 forces in an equilibrium. So, when the number of forces involved is more than 3 forces and is in equilibrium, the best way to solve it is by resolving the forces into their own components since the system is in equilibrium. The resultant force acting in any direction is 0. What that means is we can use the sum of components in whether it be x or y, as we can refer from the second statement here, as 0, meaning the total will always be 0 because it is in equilibrium. Now let's take a look at some of the questions.
Now let's take a look at this basic problem involving more than 3 forces in equilibrium. We are given a concurrent force system in a state of static equilibrium featuring a 40 kN force pointing left, a 24 kN force pulling straight down, and an 18 kN force acting at a 25 kN. Our goal is to calculate the magnitude of the unknown force T and find its angle theta. By mapping our vectors into a standard Cartesian plane where right is positive x and up is positive y, we can solve this systematically using a component breakdown. We look at where each force sits. The unknown force T sits in quadrant 1, giving us positive component. The 18 kN force is in quadrant 2, meaning its horizontal component is negative, while its vertical component is positive. The 40 kN and 25 kN force lie directly along the negative x and negative y axis, respectively. By setting the sum of all horizontal force to 0, we establish our first equilibrium equation, where T cos beta minus 18 cos 25 degrees minus 40 equal to 0. Isolating our known terms show that the net known horizontal force pushing left is approximately 56.31 kN. Next, we do the same for the vertical forces. Setting the sum to 0, where T sin beta plus 18 sin 25 degrees minus 25 equal to 0. Moving the known numbers to the other side reveals that the net known vertical force pulling down is approximately 17.59 kN. Now we solve the system of equations. Using the tangent identity, we divide the vertical component by the horizontal component. They give us tan beta equals 17.59 divided by 56.51. Taking the arctangent gives us an angle beta of approximately 17.2 degrees. Finally, we substitute this angle back into our sine equation to find the magnitude of force T. This calculates to 17.59 divided by sine 70.2 degrees, by giving us 59.03 kN. And there you have it. Our final required values are an unknown force T of approximately 59.0 kN, 03 kN at an angle beta of 70.2 degrees.
Now let us conclude today's video. In conclusion, this case study demonstrates the importance of the principles of equilibrium in ensuring that a body remains stable under the action of multiple forces. By identifying all the forces acting on the object and applying the conditions of equilibrium, where the sum of all horizontal or the sigma fx equals to 0, the sum of all vertical forces, which is sigma fy is equals to 0, it is possible to determine the unknown forces and verify whether the system is in equilibrium or not. The analysis shows that proper force balancing is essential in engineering and everyday application, as it helps prevent unwanted movement, structural failure, or instability. The calculations also highlight the value of accurate free body diagrams and systematic problem-solving techniques in obtaining a reliable result. Overall, the study reinforces the practical application of engineering mechanics and demonstrates how the principle of equilibrium are used to design safe, stable, and efficient structures and mechanical systems. Thank you.